Electric shielding. For this, I want to start with a few questions. So first of all, what do you remember about like charges? Like charges. With that, you probably remember that like charges repel. And so when we talk about electrons on a negatively charged object, what we can assume is that those negatively charged electrons are going to be repelling each other. Meaning, if we have a conductor that's negatively charged, those electrons are going to be repelling each other. Those electrons are going to be spreading out across that conductor in a way so that they are as far away from each other as possible because they are like charges. Now, if we have a conductor that is an empty shell, which I'll show you in class, what this causes is the electric field inside of that conductor is going to cancel out. And so there is no electric field essentially inside of that conductor. And this is what we call electric shielding. This is what we use to shield electronics from outside electromagnetic radiation. It's what we use for Faraday cages, things like that. And so what happens is the outside of that conductor will have an electric field, but the inside, because of the conductor, it will cancel out. It doesn't matter the shape of the conductor. In fact, depending on the shape, you can have a different concentration of charges, which I'll show you in just a little bit. But with the shape and the concentration, they will still cancel out on the inside, but not necessarily on the outside. If you've ever seen videos of a car being hit by lightning or of an airplane being hit by lightning, the charges typically stay on the outside of the car. So if you are driving and you're going through a lightning storm, you don't want to get out of the car. You want to stay inside of the car because the car essentially is going to be a Faraday cage for you, and it will protect you if you're on the inside. If you're outside of the car, you won't have any shielding, and you could easily get hit by lightning if you were in that situation. If you've ever seen demonstrations with huge Van de Graaff generators, sometimes there's a person that is inside of a cage, and you can actually see this person touching the inside wires of that cage, and it's because the charges distribute on the outside of the cage because of this shielding effect. All right, let me show you a diagram. This is a drawing of the electric field if we have a charged particle. In this case, this is going to be positive because you can see the arrows are going away from it. And also with the concentration of the negative charges, you can see that if we have a conducting sphere and we have a positive charge getting close to it, this will induce the electrons to move more to the right side. And you can see the electric field concentrating there. And because the electrons are going to concentrate over on the right side, the left side is going to be induced to have a positive charge, and so you can see the electric field over there. What you also notice is the inside of this conductor has no electric field because with the way these electrons are going to be organized on this, the field on the inside essentially cancels out. Okay, so this conductor is oddly shaped and is positively charged, so electrons have been removed from it. And so what do you notice about the concentration of charges? You'll notice that it concentrates towards the peaks, where the radius of curvature is the smallest. Now, what you want to be careful about is when we talk about something that is positively charged, we have not added protons. What we have done is we have removed electrons. So you might be thinking, well, how come we have positive charges that are distributed unevenly? And the way to really think about it is, it's not that the positive charges are distributed unevenly, it's the electrons are distributed unevenly. And we have a net loss of electrons. And so the electrons will redistribute themselves around here in a way so that the positive charges look like this. Now, if we have it as negatively charged, you can see it a little bit more here, and this is going to be all over on the surface. And you can see that the density of the charges go like this. So where the radius of curvature is the smallest, you have the densest charge. Where the radius of curvature is a little bit larger, it's going to be a little bit less dense. And where there's very little radius of curvature, almost straight, it's going to be the least dense in terms of its charge. Now what's going to happen is if we were to draw the electric field inside of this, there would be no electric field. It would all cancel out on the inside. What you can see here is how the field lines would be drawn for something like this. And these are equipotential lines, so the lines are equally separated by their strength. So that is electric shielding. You have a conductor. The outside has an electric field, but the inside, the field has essentially canceled out.